So we want number 9 or number 10?
9.
9, okay. Okay. So they want to know, or they want to list the actual data entries, want to know the maximum data entry, the minimum data entry. So what is the smallest value?
27.
Got to make use of the key to determine the numbers or the interpretation of the observations. So based on the key that is provided, what is the minimum value?
47.
What is the maximum value?
85.
Most of the numbers occur around 50. So somewhere over here. Towards it. So interpretation is fine. Should we go with this or pick up an example and create our own standard?
This.
This?
Yes.
Fine. I thought you guys would say create our own. Oh well. So let's go ahead and write the data observations. Those are the data, excuse me, that is the stem and leaf plot. Now we're going to switch over to the data points and I'll show you how to create a frequency distribution this time for real. How the textbook does, so that you don't make a mistake in my maths lab. Got to move the camera. So well, in order to create the frequency histogram, we need to find the minimum value and the maximum value. So what is the minimum value? It is 27. So the maximum value is 85, the minimum is 27, divided by, let's say, I think 6 classes would work. Go 5. 5? Yeah. So I'm telling you that 5 classes is what we're going to go with. That would come to 11.6. Regardless of what number you get there, you always round up. So that part is great. So always round up. So we'll put it.
You get 11.1.
11.1.
What if you get 11?
What part of always round up did you not get, Alex?
Okay.
Wake up.
I found in my math lab though, it always rounds down.
Yeah, that's why I asked.
Yeah.
Always rounds down.
Yeah.
Fine. So always rounds down.
No.
I said it always rounds up.
Look,
No,
I did the first exercise and gave up, but the class width was like.
So you always round up. You guys are supposed to read and correct me. One person did and came to my office at 8 in the morning. Well, it was half wet. It's hard to figure that. But it's a great job there. So we have 12. The key difference between what we did and what my math lab is supposedly doing, or actually doing, is this. What is called data. 27 is the upper limit, yes?
Yeah.
And it's adding 12 to, excuse me, lower limit. It's adding 12 to each of the lower limits. So 27 plus 12, 39. 39 plus 12, 31. 31 plus 12, 63. 63 plus 12, 75.
That's five,
What?
that's five classes.
Come again?
That's 5 classes.
But we want 6, right?
Why are we
You-
on top?
you-
Oh, that's fine.
Wait,
You said
You said five
classes.
classes,
So it should stop here. Why is it not working?
because then from
six.
75 to 87,
So it should be,
27 plus
that's the
12.
lower,
that's.
39.
It's because on the last one, you're gonna
Never
go from
mind.
75 to, yeah.
Oh,
yeah.
yes. So 37, 39, 51, 63, 65. So we are adding plus 12 there, plus 12, plus 12, and the upper limit is 1 less. So 38, 50, 62,
That's, it should
74.
be 40.
no,
No,
Wait, then why do you have it?
1 less than 51.
Oh, my bad.
And 75, 1 less than 75 is 74. The last one, just have to add
86.
63 plus 74 is 11, so that would be 86. So that is how they do it. Now you may say, well, what would happen to all of the problems that we did with the inference being different? No. If you go back and try with this approach, use the same number of classes, there will be subtle changes, but it's not going to change your inference much. That's why we say most of the frequency distribution methods that we have are very close to each other. Does that make sense? So I'm doing this for the sake of my math.
Isn't that the same thing that we did though?
No.
if it's,
So last time we added here
Every
and
13.
then pick the next number.
Oh.
So it's okay. Stick with this. This is the my math approach.
Very clear.
So you don't want us to do it your way?
I would love for you to do it my way, but MATLAB is not going to accept. So do you want to get it right or not? So if you want to get it right, do this way. On an exam, I'm not going to ask you to construct a frequency distribution, so don't worry about it. Inference is what we need. So now we count the corresponding frequencies, 27 to 38, 1, 2, that's it. Isn't it nice that we've got the data from stem and leaf plot? What is the advantage?
it's in order.
It's in order, we don't have to go all over the place. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. One, two, three, four. 1, 2, 3. Good, yes.
If you did it this way versus your way, would you still get the same answer?
So it's different slightly. That's why I'm showing you this way so that you don't, even the slightest mistake could avoid. It will differ slightly. But when I say the inference will be the same, you know, the ogive we got, the relative frequency polygon we got, the pictures will be the same. The values that you put in the bottom will change by a bit. That's it. So if I sketch this as a frequency histogram, what do we need?
Midpoint.
Midpoint.
No.
Histogram,
Mhm.
to subtract and add.
Subtract and add
Wait,
to get
The boundary.
The
the boundaries.
boundaries.
Okay,
That's one.
26.5. 38.5. 50.5. 62.5. 74.5. Running out of space. 86.5. Two for the first class, 8 for the second, 15 for the third, 4 and 3. We can go to 0. Good. Do we see a shape? What shape?
About
Bell curve, the bow of statistics. So if you don't see the shape, what do we do to get a better picture? Draw a line. Okay, what is that called?
the midpoint.
Yes, you connect the dots, but to get. No, you use the midpoint to connect the dots. What is the line?
Or
The relative.
So close, no. Relative frequency polygon. Who says that? Ray, what's your name? Michaela, be like Michaela.
I'll try.
Okay, so we want to find the midpoint. Does it matter whether we find the midpoint here or there?
No.
No, we'll get the same answer. How do we find the midpoint? Average of what? Okay, so 38 plus 27 is 65. 65 divided by 2.
5.5. Wait, what? 32.5. 5.5, so yeah, to that.
Likewise, 15 plus 39 is 89. 89 divided by 2 is
44.5.
okay. Good. So we are pretty much adding 12, right? So I was at 32.5. I add 12, I would end up getting 44.5. Add 12 again, you would get 56.5 and so forth. What is 12? 12 is that magical number that we rounded up always. Now we can connect the dots. We're not connecting these. Absolutely. So dot, dot, dot. Yes. So we will have good. Now that looks like a bell curve of sorts, correct? So we're able to get a nice little curve using the data that we got from the stem and leaf. Yes.
And then the class fifth, for example, if you want to find out, you take the 50.5 minus the 38.5.
Yes. Most of you got it. It's a great thing. Now, it would be silly for us to ignore the decimal because we would lose information. Yet at the same time, if we had too many decimals here, that's going to create problems, right? Which is why I mentioned last time that stem and leaf plot is not a good candidate for continuous data. So one decimal place we can deal. So the best way to define the key, 4 vertical down 3 would mean 4.4. Good. So the stem part and the leaf part. Fortunately, it's not in order. So 4 goes first. And what do we have? 3 and 9.
3 and 9.
3 and 9, that's it. 5 goes next.
1,
1, 8, 8, 8, 5. 5.
And there's a 9, and there's a 9 too at the end.
6.
4, 8,
4,
9,
8,
9.
9, 9, 9. 7. We've got 0, 2, oh, 0, 0, 2, 2, 5.
No,
There's
another 2.
two, three.
There's 3, 2.
You missed it too.
There's 3 twos.
And lastly, 8, we have
0.
0.
0.
And 1. And 1.
Do you think that's sort of bell curve?
Yeah.
Or if you
Kind
angle
of.
your head in the right way.
Kind of skewed.
If I turn my head the right way, I can make it
Yeah.
normal. That is actually true, depends on the angle.
How big you write the numbers.
That's it. So, you know, sort of normal, I guess. But in practice, we have ways to determine if the data is normal or not. Good. Now, this is great and all. But if we had more than 2 decimal places, of course, it's going to cause a problem. In the sense, if I have 5.82, it's going to be hard, either, for me to put 82. Like, in that case, I'd have to multiply by 10, move a decimal, and then write the key, and then put a note below that we moved the decimal, one step. It's too much work. That's why Salmon Lake was a great candidate for a small quantitative discrete sum. Others, not necessary. Are we clear? Okay.